See this one. A frame consists of the members as shown in the figure. There are 5 members that are available. All the members are 125 mm, like all the tension members are 125 mm square, and the compression members are 250 mm square in area. Find the vertical deflection at point C. Okay. So just understand here, before solving this problem, we have to consider the free body diagram at each joint to get the forces in the members. Here, C is a free end. That's why what you can do is initially you will take a free body diagram at C, and these forces will be calculated. Force in BC, force in CD. Then the next step, what you will do, either you have to go with the joint B or you can go with the joint D. As B is a support here, the support reaction is to be calculated. So before calculating this support reaction, you can move to joint D. Okay. At joint D, these two forces you will calculate. But how to get the force in AB? Force in AB, how can we get it? So to get force in AB, there is no other alternative. We have to either take joint A as a free body diagram at joint A, or free body diagram at B. Here the reactions are not yet calculated. So to get the reactions here, first of all, in this step, for this problem, calculating the reactions is very, very important. So for this purpose, first once again draw the frame. As this is a roller support, one vertical reaction is there, that is whereas here one horizontal force as well as one vertical force will also be there here. So why I am calculating the reactions of this one is, here to get the force in member AB, either you need to take free body diagram at A or free body diagram at B. That's why the reactions are to be calculated initially. Here in this case, how to calculate the reactions? What is the distance from here to here? This distance is to be calculated. So this is 0.5 meters, and this distance is to be calculated, vertical distance. To get the vertical distance, just take it as this vertical distance. You can calculate this vertical distance as square root of 1 square minus 0.5 square. 1 square minus 0.5 square. What is the value? So this is 0.866 meters. Now similarly, this distance is also 0.866 meters. So what we calculated here, the vertical distance, this is the vertical distance from A to something like C dash or B dash. The distance is calculated here. This is 0.5 meters. This is 1 meter. So considering it as a perpendicular triangle here, this is 1 square minus 0.5 square, which is 0.866 meters. Considering sigma fx is equal to 0, there is no horizontal force, so RAX will become 0. RAX will become 0, there is no horizontal force. Sigma Fy is equal to 0. There is vertical forces plus RAY plus RB equal to, there is minus W equal to 0. There is RAY plus RB equal to W. Now taking a moment about A is equal to 0. Here understand, I am considering these equilibrium equations to get the reactions. Whereas at a joint, if you take the free body diagram, you will be having two equilibrium equations. Sigma fx is equal to 0, sigma fy is equal to 0. That is for each individual joint. Here for the entire system, you are calculating the external reactions. So this is taking moment about A is equal to 0. Your RB is making anti-clockwise minus RB into 0.866 plus W into, this is 0.866, this is 0.866, is 1.732, I think. 1.732 is the distance is equal to 0. That implies RB is equal to 2 into W. Is it correct? So RB is 2 into W. Is it yes or no? Now, after getting this, go to the above equation, sigma Fy is equal to 0. That is RAY plus 2W is equal to W. That implies RAY equal to minus W. So the reactions are first calculated here. Now, to get the forces in the members, go to the free body diagram at C. Now, calculate free body diagram. C. So to get the free body diagram, just let me wait if you have completed it or not. So in the first step, what we have done is the reactions are first calculated by considering the equilibrium equations for the entire system. Remember, if you go for a joint, at a pin joint, the available equations of equilibrium are 2. But for the entire system, if you want to get the reactions, external reactions, then for the external reactions, the available equations of equilibrium are 3. If this is completed until this portion, let us move to the next portion, calculating the free body diagrams at each joint. So now here, drawing the free body diagram at each joint. Now coming to the joint here, this is C. Downward force W is acting here. This is force in CD. This is force in BC. Now here, this angle, entire angle is 60 degrees. So this is 30. This is 30. Total entire angle is 60 degrees. So that is 30. This is 30. Is there any other force that is acting at joint C? No. CD is one force here. BC is another force, and W is the downward force acting. Now, resolve them along x-axis as well as along y-axis. So this FCD is FCD cos 30, FCD sin 30. while for FBC, this is FBC cos 30, FBC sin 30. Now write down sigma Fx equal to 0. That implies minus FCD cos 30 minus FBC cos 30 equal to 0. So that is minus cos 30 can be taken as common, and 0 by cos 30 is 0 only. So this is FCD plus FBC 0. FCD plus FBC is equal to 0. While sigma Fy equal to 0. Minus plus FCD sin 30 minus FBC sin 30 minus W equal to 0. In the above expression, I can say FBC can be minus FC. So substituting this in the below equation, FCD sin 30 minus of minus FCD sin 30 minus W equal to 0. That is minus into minus plus, which is 2FCD sin 30 equal to minus W on the right side will be plus W. So sin 30 is nothing but here this can be written as 1 by 2. This sin 30 is 1 by 2, 2 to cancel. So FCD will become, and as FCD is capital W, this implies FBC is minus W. So this is under tension, whereas FBC is under. Check this, whether you people got the same answers or not. Right, good. If I am explaining quickly, just you can stop me and ask, sir, please repeat once again if you are unable to do it. Otherwise, we'll continue further. Now, let us take the free body diagram at D. So, free body diagram at D. Here, a downward force is there, which is force in BD. This is force in CD. This is force in AD. So, this is joint D. That's it. Now, this is making an angle of here. This is 60 degrees. Or, with respect to what horizontal, this is 30 degrees. This is also with respect to vertical, this is 60. With respect to horizontal, this is 30 degrees. That is 30 degrees. Now resolve the forces. Inclined forces are to be resolved along horizontal as well as along vertical. FAD cos 30, FAD sin 30. Now sigma Fx equal to 0, CD and plus W cos 30. So FAD is equal to plus W, which is potential. Sigma Fy equal to 0. Minus FAD sin 30 minus FCD sin 30 minus FBD equal to 0. So substitute the known values here. This is minus W sin 30 minus W sine 30 is equal to F of FBD is equal to minus 2W sine 30. Your sine 30 is 1 by 2. So this is nothing but minus 2 into W into 1 by 2, which is minus W. So force in BD is minus W, which is no. Just check it whether you are able to solve it or not until this. And take free body diagram at B. The next step, take free body diagram at B. So this is a B, a reaction or is there. This is a force in BC, force in AC, force in BD. In this case here, the angle made by these members are nothing but from here to here, this is 60 degrees. 60 degrees. So this is 30 degrees. This angle is 60. This is 60. So the horizontal angle, this is 30 degrees. This is 30 degrees. And what is the reaction value RB? I think it is 2W. RB is 2W. So this one is 2W. Now the inclined forces are to be resolved along x-axis, which is FBC cos 30, FBC sin 30. And this is FAC is there, so FAC cos 30, FAC sin 30. So sigma Fx equal to 0. Summation of the forces along x-axis minus FAC cos 30 plus FBC cos 30. So FBC, what is the value of FBC that we got? Minus W. So minus FAC cos 30 minus W cos 30 equal to 0. So cos 30 can be cancelled. FAC is minus W, which is the indication of. Yeah, Shweta, any doubt from your side? Raise your hand, ma.
Yes, sir. Sir, AB na AC na sir.
Either ma. That is AB, na? Okay, wait. Just wait. Yes. That is AB, right? Yes. Make a correction of this one. Yeah, this says nothing but FAB. So this is FAB cos 30. This is also FAB sin 30. So after resolving the forces here, along x-axis, this is minus FAB cos 30 plus FBC cos 30 equal to 0. So cos 30 can be cancelled, and this is FAB is equal to FBC. So FBC is minus W, which is the forces in the numbers are calculated. Now let us go to the tabular form. Serial number. Here, the area of the cross section of the numbers are given. So length, area, square, length in force newtons, square L by 2AE. Here coming to E, what is given in the question regarding Young's modulus of the material? 200 kilonewton per mm square. 200 kilonewton per mm square. So here E is equal to 200 into 10 cube Newton per mm square. So E is 200 into 10 cube Newton per mm square. All the forces we are considering in terms of mm. Now the members are 2, 3, 4, 5. Now the length of the members here is given as 1 meter, that is nothing 1000 mm. All are of equal length, so they are 1000 mm. Area is nothing but, so from the force you will get the area. What is the force in AB? AB is minus, you just got it here. So BD minus W. BD minus W. AD plus W. CD is W, BC is minus W. CD is W, BC is minus W. Now it is said in the question that tension members are having cross-sectional area of 5, 125 mm square. So write down tension members are 125 mm square, whereas compression members are nothing but 250 mm square. So here 2 are in tension, remaining 3 members are in tension. And this is also 250 mm square. So this is nothing but force P square L by 2AE. So substitute the values here and get the value in terms of W. So this is minus W whole square. You will get it as W square. So one coefficient you will get, that is length is 1000 by 2 into, so the value is nothing but, how we are going to write here, minus W whole square into 1000 by 2 into 50 into 200 into 10 cube. 200 into 10 cube is the value of E. Cross-section area is 250 for compression member. So here this 10 cube 1000 can be cancelled. So what is this value? Similar way, substitute here W square into into 1000 by what is the value of this one? 80. W square into 1000 by 2 into 25 into 10 cube. So 10 cube, 10 cube cancel. So what is this value? Minus 5 into 10 square. This is 10 power minus 5 into 10 square. 2 into 10 power minus 5. A total of sigma e square L by 2 AE is nothing but 7 into 10 power minus 5 W square, which is nothing but the strain energy factor Q. You would like deflection at C, that is nothing but 2 by 2 into 7 into 10 power minus 5 into W square by W. So this is nothing but 14 into 10 minus 5 W. The W is the load. Whatever the load you will substitute, corresponding deflection at C can be calculated. This is how we solve a problem for deflections in a pin jointed. Remember, this is applicable for pin jointed frames where the members are subjected to only either axial tension or axial compression. Let us go to the next type of problems. Till now, whatever we have seen is we have seen how to calculate the deflections in a pin jointed frames. Now, in a pin jointed frames, what happened? The members, they will be subjected to axial tension. So considering the axial tension, the strain which is stored in the body is represented as P square L by 2 AE. So using that, we calculated what is the deflection at a particular point. Now we'll see other problems where through bending, the strain energy through bending, using that concept, how to calculate the deflection under the rules. Okay, so just note down the another point. A simply supported beam of span L carries a point load W at a distance of A and B on both ends. Determine the deflection under the load. Determine the deflection under the load. Now this is the beam. Which is being subjected with a concentrated load of W at a distance of A from left end and at a distance of B from right end. And the entire span of the beam is L. Now it is asked to calculate what is the deflection under C. So for this, first of all, we will calculate what are the reactions of this beam. To get the reactions, draw the free body diagram. So free body diagram is nothing but replace the reactions with the unknown forces. Here at A, as there is no horizontal force at this hinged support, Only one vertical reaction is there. At roller support, one vertical reaction is there. This is A and B. The total length is capital L. Sigma Fx is not applicable. Sigma Fy equal to 0. So for this one, sigma Fy equal to 0, Ra plus Rb equal to W. Taking moment about A is equal to 0, that implies minus Rb into L, which is anti-clockwise, plus W into A. So which is nothing but W A by L. Rb value is W A by L. And substitute this in the above equation. Ra is nothing but W minus W A by L, which is nothing but L minus A by L. So L minus A is nothing but B only. Minus A is nothing but B only. Hence, this is W B by L. RA value is equal to here W B by L. RB is W reaction. So here A to C is one particular type of bending moment will be there, C to B another one will be there. Why? Because wherever there is a point of application, there is you have to divide the entire beam into two portions. C portion as well as CB or BC portion. Now see in this, the strain energy is nothing but this is applicable. The strain energy is nothing but corresponding to bending. The previous cases, that is for axial forces, but here this is due to bending. So strain energy due to bending is nothing but m square into L by 2EI. That is the strain energy. But if we are considering for a small element and upon integration 0 to L, m square into dx by 2. We have written this in the previous classes. Strain energy is nothing but integration of 0 to L, m square into dx by 2EI. Now take this, calculate the strain energy for AC portion. So we are first calculating for AC portion. So in the AC portion, what we will do is to calculate this. What is the length of this AC portion? This is the integrated upon a length of 0 to A. It is not for the entire length. Why? Because we are considering there is a change in the loading pattern at C. That's why portion AC is separated, portion CB is separated. From 0 to A, m square into dx by 2. Here, understand. AC portion is there. Consider a free body diagram. That is, consider a section at a distance of x from A. Take the left side free body diagram. Left side free body diagram means cut the section. This is the section. This distance is x. And the value of this one is WB by L. This one is A. Now, what is the moment at this one? At the section XX, what is the moment? Just understand this one carefully. Please understand this. Here, this force WB by L is giving a sagging moment. Is trying to push the upward direction, which is giving sagging. So sagging is positive, sagging is negative. So the moment at section xx is nothing but plus wb by l. X is the distance, force into distance. So wb by l into x. Substitute that in this equation, which is 0 to a, 1 by 2 ei is constant into wb by l into x square. In this, ei is constant, wb by l is also constant. Only the variable is 0 to a x square into dx. And this is wb by 2ei into l. wb by 2ei into l. Now, in this case, here, x square, can any one of you tell me what is the integration of x square? L into x cube by 3, and this is 0 to a. The limits are 0 to a, and this will be w a cube b by 3 into 2, 6, 6 I. Yeah. Just make a correction here. Just we forgot one point here. This is wb by l whole square. So w square, b square, and l square. W square, b square, l square. W square, b square, l square. You should not forget all these things. So that is w square a cube b square by 6 ei l square. This is the strain energy for AC portion. Similarly, C for BC portion also. That is strain energy for BC portion is nothing but integration of 0 to B. The origin is we are considering from the right side. So 0 is this point, B is this point, 0 to B. Integration of 0 to B, m square into dx by. So in this case, see, once again draw the free body diagram. So how you are drawing the free body diagram? Cutting the section at distance of x from the origin. The origin is considered as B. B is the origin, and take the free body diagram towards right side. So simply see, I am cutting this section, and this portion is to be taken. This portion is considered as our free body diagram. So this is RB, and RB value is W A by L into X here. This point is B. This is XX section. Now, what is moment at XX? Moment at any point is nothing but this is also creating, is giving sagging or hogging. Is trying to push the beam like this, which is sagging, positive W A X by L. W A X by L. Now substitute this 0 to B plus W A X by L whole square dx by L. So the strain energy in BC is nothing but this is W square A square by 2EIL square 0 to B x square into dx. So this integration from 0 to B x square into dx. W square A square by 2EIL square into x square derivative is x cube and the limits are 0 to B. Now, the total strain energy. This is for two portions, AB portion as well AC portion as well as BC portion. Total strain energy U is nothing but U AC plus U BC, which is W square AQ square by 6 EIL square plus W square A square B cubed by 6 EIL square. In this, just take a common of W square A square B square by 6 EIL square. In this, A is taken common plus we know that A plus B is nothing but what is the value of A plus B? L only. A plus B is L only. So U is equal to W square A square B square by 6EI L square into L. A plus B, you can refer it as L. So L, this will be cancelled, which is W square A square B square by 6EIL, which is nothing but the strain energy stored in the body due to the application of a point load W at point C. So this we call it as internal strain energy. We know that internal strain energy is equal to external work done. So external work done, what is the external work done? So when you apply a load, due to the application of the load, certain deflection will occur. So load into deflection is the work done. And we have already derived that this load is gradually applied. So the triangular area under the curve will be considered as your work done, which is R. That is external work done. Internal strain energy is your U. Implies delta is equal to 2U by W. So 2 into your U. Strain energy is nothing but W square A square B square by 6 EI into L by capital W, which is nothing but W A square B square by 3 EI into L. Delta is equal to W A square B square by 3 EI into L. This is the deflection. This is the deflection vector C. So using strain energy due to bending, we calculated what is the deflection. So your problem is beam is there here. Here what is given at a distance of a load is acting, and this is B, as it is a simple supported beam. So what is the deflection? So from the strain energy concept, we got deflection as W A square B square by 3 EI into L. Instead of A and B, if the load is acting at the center of the beam, it implies A is L by 2. Substitute A as L by 2, B as L by 2. So delta C is nothing but W into L by 2 whole square into L by 2 whole square by 3 EI into L. So this is 1 by 4 into 1 by 4. 1 by 16 into 1 by 3, which is 1 by 48, and L square into L square is to the power 4 by L cube. So that is W L cube by 48 EI. You already know this one, right? So from your double integration method or conjugate beam method or moment area method, we know how to calculate the deflections in a beam. Now using strain energy concept also, we can calculate what is the deflection. Similar way, we can also calculate what is the rotation at a particular point. That we will see in the next classes. So as of now, this is the procedure how to calculate the deflections in a simple supported beams. Using strain energy concept, we are calculating. So the strain energy is, if due to bending, is nothing but integration of 0 to L m square into dx by 2, right? So I hope you understand this concept. We'll try to solve as many problems as possible in the coming classes.